Hello everyone, this is Aisha. So today we'll start with the chapter phase rule, which is there in physical chemistry, right? So here we'll start with the phase rule. So this phase rule is basically used to study for the heterogeneous system, and here with the phase rule we can predict the phase diagram with the effects of temperature, pressure, and concentration term. Next year, this phase rule was given by the scientist whose name is J. Willard Gibbs in the year 1876, and he states that, or you can say he defined the phase rule as the sum of the number of degrees of freedom and the number of phases exceeds the number of components by 2. And he had given the equation as F plus P is equal to C plus 2, where F is called as the degrees of freedom, P stands for the phases, and C stands for the number of components. So based on these three terms, he had given the statement for the phase rule as it is the sum of the number of degrees of freedom, number of phases exceeds the number of components by 2, right? So this equation is called as the phase rule equation. So just by rearranging, we can determine the number of degrees of freedom is equal to C minus P. So here this P is actually plus, right? So when you shift toward this side, it becomes minus. Therefore, you'll get minus P plus 2. So this equation is called as Gibbs phase rule equation. That is F is equal to C minus P plus 2, right? So here we have defined the phase rule. Now before starting with the actual systems, we will learn few terms which are involved here. Like we'll study about the degrees of freedom, number of phases, and what do you mean by the number of component. So here we'll start with the terms involved in phase rule. And that the first we'll start with the phase. So here phase is defined as any homogeneous and physically distinct part of the system which is separated from other parts of the system by definite boundary surfaces, right? So this is a definition for a phase. So in simple words, we can say a phase which is a homogeneous and physically distinct part of the system. For an example, when we take a glass of water, so here in a glass of water, you can see it is a homogeneous mixture, right? And here it gives you only one phase, or you can say only one layer. In the same way, when we take an example of oil plus water, right? So here that is oil plus water gives you two layers, which is not a homogeneous phase, right? So phase is defined as any homogeneous and physically distinct part of the system which is separated from the other parts of the system by definite boundary surfaces. In simple words, you can remember like phase is nothing but which are represented with the layers, right? So that is the definition for a phase. Now we'll discuss a few examples for the phase, like when you take one or two or more miscible liquids which form only one phase. For an example, when you take in water along with ethanol, it gives you only one phase. Means it is give you a miscible liquid. Miscible is nothing but which is soluble, right? You will get only one homogeneous phase for ethanol and water. As it is giving you only one homogeneous layer or one homogeneous solution, therefore we'll say it has only one phase, or in simple words you can say it has only one layer. In the same way, when you take another example, such as when you take two or more liquids, such as water plus benzene, which are immiscible. Already we know immiscible is nothing but which is insoluble, right? So this water plus benzene forms two layers, ultimately give you the two phases. In the same way, we can take one more example, that is by taking three liquids which are immiscible, which are insoluble, form three phases. For an example, when you take water along with benzene plus mercury, right? We have taken three immiscible liquids, therefore it gives you the three phases, right? So these are the few examples which you can give under the number of phases. And one more general example we can take, the best example, that is when you take water in the liquid form and other in the solid form. Solid form in the sense like you can take an ice. Ice plus liquid water gives you the two phases. Why? Because in a glass, when you add some ice and into that, when you add some water, what happens easily you can distinguish the two layers, right? We can observe homogeneously, physically distinct part. That is, one is for the solid part and another one is for the liquid part. So here the number of phases for this example, that is for ice plus normal liquid water, will be 2. So that is the explanation along with the examples we can give for the phase. So in short, phase is nothing but which deals with the homogeneous and physically distinct part of the system which are separated by a definite boundary surfaces. Right? So that is called as a phase. Now we'll move with the next term, which is called as the component. Right? So component is defined as the smallest number of independently variable constituents by means of which the composition of each phase can be expressed by means of a chemical equation, right? In simple words, you can say component is basically deal with the chemical composition, basically deals with the chemical composition. So here to understand more clearly, we'll take one example. That is, let's take the ice in the form of solid, liquid and vapor state. So here solid, that is ice, sorry, we'll take one example of water in the form of solid, liquid and vapor state, right? We have taken three different states. So as we have taken three different states, you can easily see there are three phases. One is for the solid, another one is for the liquid, and the third one will be for the vapor state. So easily the number of phases will be three. But when you see the component, as component is defined as which deals with the chemical composition. So when you take an example of water in the solid, liquid and vapor, whether the states are different, but its chemical composition remains the same, right? In all the three states, it's of water only. So therefore, the number of component for this example will be is equal to 1, right? So for this example, the number of component is equal to 1. So in the same way, when you take another example, such as the calcium carbonate dissociate to give calcium oxide and carbon dioxide, right? So when you observe its states, so here calcium carbonate, it is in solid state, calcium oxide is also in solid state, whereas the carbon dioxide in the gaseous state. So here when you see the number of phases, the number of phases will be 2. One is for the solid, another one will be for the gaseous state. So number of phases is equal to 2 in this particular example, and here the number of component also is equal to 2, because here we are observing two different chemical composition. In the same way, when you take one more example, that is dissociation of ammonium chloride, which dissociate to give ammonia and HCl gas. So here the number of phases again will be 2. Why? Because one is for the solid, another one is for the gaseous state. So number of phases will be is equal to 2. And the number of component will be is equal to again is equal to 2, because you are observing the two different chemical composition. So overall, to define a chemical component, in simple words, you can say chemical component deals with the component deals with the chemical composition. Components deals with the chemical composition, whereas the phases means which are the homogeneously physically distinct part of the system separated by the definite boundary surfaces. In simple words, you can remember phase means which can be easily distinguished by seeing the layers, whereas component which deals with the chemical composition. Based on the chemical composition, we can say how many number of components are present in the given solution. I hope it's clear both the terms. So now we'll proceed with the third term, that is called as the degrees of freedom. So here the degrees of freedom is defined as it is the number of variable factors such as temperature, pressure, or concentration, which must be specified in order to define the system completely. Right? This is the definition given for the degrees of freedom. So, in simple words, you can remember as that for degrees of freedom, right, deals with the number of or depends on the variable factors. The variable factors can be temperature, pressure, concentration, composition, any one of the, like any it can depends on any number of variable factors. So overall this degrees of freedom depends on the variable factor. So in here to get more clarification, for here we'll take one example, that is one component, one phase system. Here under one component, one phase, we'll take a specific example of pure gas. So here gas depends on the two variable factors. Already we know vapor state depends on the two variable factors, that can be temperature and pressure. Right? So it can be temperature and pressure. So as it depends on the two variable factors, therefore it is called as a bivariant system. And here the degrees of freedom will be is equal to 2. F will be is equal to 2. In the same way, when you take another example, that is two component, two phase system, where we'll take an example of water which is in contact with its vapor. And here this particular example gives you or depends on only one variable factor. Therefore, it is called as a monovariant, where F value is equal to 1. So overall in the third term, that is under the degrees of freedom, we can remember one point, that this F value depends on the variable factors, right? So I hope it's clear all the three terms which are involved in the phase rule equation. That is a phase, second term was component, third term is degrees of freedom, right? So I hope you have understood today's class. So if you like, you can subscribe my channel. Thank you for watching, and